Welcome to Dunwoody College of Technology, Mechanical Engineering 2240, Mechanics of Materials. We're working through a solution to Hibbeler problem 923. This is a stress transformation problem. So we're given this piece of wood that has an applied axial load of 250 newtons on it. We're given the cross section of the wood and the orientation of the grain structure. So we're told that the grain structure of the wood makes an angle of 20 degrees with the horizontal, and we're asked to find the normal and shear stress that act perpendicular and parallel to the grains if it's subjected to this load. So what do we need to know here? We need to know a few things. We need to find our normal stress. So in the x direction, make that x, I'll make this y. The sigma x is going to be our normal stress if I section this somewhere. So it's going to be our normal over our area, and we don't have any bending going on. If I did, I'd add that in. In the y direction, the vertical direction, there's nothing pulling up on this or that. So sigma y is going to be 0. And in our original configuration here, tau xy, if I section this here, as I look at that, I only need this normal force. I don't have any v that would be acting up. So that's going to be 0 as well. So our normal force here is 250 newtons divided by my area, which is going to be 0.025 meters times 0.06 meters. So my stress is up to 166.6 repeating kilopascal. So my original configuration here, not too exciting. My element, 166.6 kilopascal. This is 0. I drew that negative. I don't know why I drew that negative. We'll go with it. This is 0 as well. Sigma y. This is sigma x. So now we're looking for an orientation that is 20 degrees rotated from that, right? So we're going to look for how much. This is going to be our 20 degree range. We're going to that was not perpendicular. There we go. So we're going to look for that much. What's sigma in that direction, and what is let's see which way. I'll draw it this way. There's tau be acting along that direction. Right. So what do we have? Take a look at our segment here. So I just kind of drew that just a minute ago. This is going to be our in the x prime direction. Theta is from the horizontal, right, to this x prime axis. So theta is going to be 70 degrees for this problem. So sigma x prime is going to be sigma x plus sigma y over 2, our average stress, plus sigma x minus sigma y over 2 times cosine 2 theta plus tau xy sine of 2 theta. In this case, what do we have going on? Well, sigma y is 0, tau xy is 0, so this whole guy is going to go to 0. So we get sigma x prime equals 166.6 repeating plus 0 over 2 plus 166.6 repeating minus 0 over 2 cosine of 140 degrees. Plugging some values in, we get 19.5 kilopascals. So that's the first bit. That's the part perpendicular. Now we need tau x prime y prime. And that transformation was negative sigma x minus sigma y over 2 times sine 2 theta plus tau xy cosine 2 theta. So we get negative 166.6 minus 0 over 2 sine 140 plus 0 cosine 140. That goes to 0. Tau x prime y prime, negative 53.6 kilopascal. We weren't asked explicitly for it, but let's find sigma y prime while we're at it. The transformation equation is sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 times cosine of 2 theta minus tau xy sine 2 theta. Again, this guy's going to go to 0 because tau xy is 0. So it looks like it's 0. That's a sigma. We get here 166.6 plus 0 over 2 minus 166.6 over 2 times cosine of 140. So here we get, this becomes 83. This is, total thing becomes 64. Sigma y prime is 147 kilopascals. Excuse me. So if we are sketching that out on an element, we have that rotated here. Oh goodness, I got a little shifted. So we have sigma y prime, excuse me, x prime is at 19.5 kilopascal. Sigma y prime, 147 kilopascal. And tau xy is going this way. Oh, that one I drew backwards, sorry. Tau x prime, y prime, negative 53.6 kPa. So we have this one here, sigma x prime, sigma y prime here. And that would be, so, not 40, 70 degrees from our horizontal axis. So just using those stress transformation equations. And there you have it.